In this video, we're going to learn about shaped optimization using the Morpho language. You'll learn what kind of problems Morpho can solve. We'll discuss a common structure for Morpho programs, and we'll express our simple optimization problem in a form Morpho understands and solve the problem. Many problems in the field of soft matter can be expressed as shape optimization problems. Problems involving lipid membranes, swelling hydrogels, media on curved or flexible surfaces, as well as droplets of anisotropic fluids, and many more. Morpho can solve all of these. It's particularly good at dealing with systems where the properties of the system vary spatially. That's an inhomogeneous system. It's good at handling constraints, like fixing the volume or preventing part of the material from penetrating a certain region of space. It's also good at multiphysics problems, for example, coupling the behavior of a fluid to an electric field. Most programs written in Morpho for shape optimization follow the following process. We're going to create the geometry of interest, define additional quantities necessary to specify the problem, build the optimization problem itself, perform the optimization, and visualize results. In order to show this sequence, we're going to look at what's probably the simplest optimization problem we can produce for shapes, and that is looking at the shape of a soap bubble. In mathematical terms, the problem is to minimize the area of a closed surface subject to a fixed volume inside. And the solution, of course, in 3 dimensions is going to be a sphere. So to do this, we're going to begin by creating a mesh. And before showing us how to do that, I'm going to introduce what a mesh actually is. So in Morpho, a mesh is a collection of elements that can include multiple types of element. So all meshes comprise vertices. That's a collection of points in space. Many also include edges. Those are lines that connect the vertices. Many also include facets. Those are triangles or other structures that connect between a collection of points as well. So because meshes collect elements of different type, we introduce this idea of grade. A grade is simply a number, 0, 1, or 2, that refers to the dimensionality of the element. So vertices have 0 grade, edges have grade 1, and facets have grade 2. Not shown here because they're hard to visualize are volumes, which would have grade 3. Every element in the mesh is referred to by the grade of the object and also by an integer element ID. So all vertices have an ID, all edges have an ID, etc. Because meshes are a fundamental data structure, Morpho provides quite a few ways to make them, and you can also use external programs to make them as well. You can load a mesh from a file using the constructor as so. You can use any number of modules that are provided with Morpho. So this line mesh constructor produces a mesh that is parameterized by a parametric function. The MeshGen module produces a way to build a mesh out of a specified domain. You can also make meshes manually one element at a time using Mesh Builder. Here, we're going to use the Mesh Tools module, which we're going to begin our program by importing. Since we're importing Mesh Tools, we might as well import all the other modules we need. So we'll import Plot, which is going to allow us to visualize our system. We'll import Optimize, which is going to be doing the optimization. In order to make the mesh, we're going to use the polyhedron mesh constructor, which is supplied in Mesh Tools, and we're going to give it the 8 vertices of a cube. They're distributed about the origin like so. We just need to give it 8 vertices in order, and you can see that I've labeled them with their vertex ID 0 to 7 as shown. The next job is to put in the faces. So we specify faces by walking around a sequence of vertices in order. So if we look at the first one, 0, 1, 3, 2, you can see that produces the bottom face. 4, 5, 6, 5, 5, 7, 6 is the top face. Then if I continue, I just produce all 6 faces as shown. When we call the polyhedron mesh constructor, it automatically adds in additional vertices to make triangles and completes the mesh as shown. So I'm showing 2 views here. On the left, you can see all of the cube as it's been made. And just to help kind of visualize where the triangles are, we've seen that on the right. So we're now ready to construct the optimization problem. If we go back to the mathematical statement of the problem, which was to minimize the area subject to an enclosed volume, every integral in the optimization problem is represented in Morpho by some kind of functional object. The area has a functional called area, and the volume enclosed has a functional called volume enclosed. To set up the problem, we create an optimization problem, which is a container object. We need to give it the mesh in the constructor, and then we can add the functionals to it as we create them. So we'll create an area object and add it to the optimization problem as an energy. We'll then create the volume enclosed functional, and we'll add it to the problem as a constraint. We're now ready to perform the optimization, and to do that, we create a separate optimizer object and tell it to perform some optimization steps. Here, we'll tell it to perform up to 1,000 steps. We'll create the optimizer, giving it the problem of interest and the mesh, and then we'll tell it to use the conjugate gradient method to perform however many, up to n steps. It will automatically stop, based on certain criteria that we'll discuss in a later video. If we run that, we can now visualize our optimized mesh as follows. So we just use the plot mesh function. We give it the mesh. We give it the grade of objects we're interested in seeing, which is grade 2. That's the faces. We can also save a copy of the mesh for later use. And we'll see that we've got something that looks very coarse, but it's the closest thing to a sphere for this level of mesh. We're going to do better, but before doing so, let's have a little bit more of a look at what happens when we call the optimizer. The first thing the optimizer does is computes the force on each vertex due to the functionals defined. It also computes the gradients of the functionals with respect to the mesh positions. It then projects the component of force in the direction of any constraints to prevent violating the constraints to linear order, and then takes a single step. So here the vertex positions are updated based on some kind of step size or learning rate. And after this sequence, the solution is reprojected onto constraints. There are many different algorithms for optimization. This is perhaps the most basic one you can imagine, and we'll look at these in further videos. So to give you a sense of what it means to compute the gradient of the functional with respect to the vertex positions, let's have a look at a single triangle. Here's the area function. We can calculate that from the cross product of 2 sides. If we compute the gradient of the area with respect to each of the 3 vertices, we can see that the gradients themselves lie along the perpendicular bisectors at each vertex. So if we were to walk up in the direction of either of these directions, you can see all of them are trying to enlarge the triangle. This is just for one triangle, and of course then if we sum these over the entire mesh or over selected regions, that's what gives us the gradient of the functional with respect to all of the vertex positions together. Functional objects like area are really useful. They provide a variety of tools to help with optimization. They can compute the total value of the integral over a mesh or a selected region. They can give you the contribution of each element to the total using integrand. They can give you the gradient with respect to vertex positions. And in more advanced problems where we're not just dealing with meshes, they can give you the gradient with respect to other quantities as well. We'll see some of those in future videos. The next step to improving the quality of the solution is to refine it. Refinement generically means replacing elements of a mesh with new, smaller elements. And so this is a multi-stage process because meshes in Morpho tend to depend on other data structures, and so we have to make sure. And so in order to do the refinement, we create a separate mesh refiner object. We give the mesh refiner a list of objects to refine. Here we only need to refine the mesh, and so we just give it the mesh. And then we call the refine function on the mesh refiner. This returns a dictionary that maps the old objects to the new refined objects. We can use this dictionary to update the problem and the optimizer by just calling their update methods. And finally, we need to make our variable m refer to the new mesh, and we do that by just finding the corresponding value in the refmap dictionary. If we take the original mesh on the left and we refine it, you can see that all of the triangles have been replaced by new smaller elements. However, it's still the same shape, and so then we need to optimize it. What we can do is redesign the main loop to iteratively optimize and refine. So this is our new loop. You can see that we'll perform conjugate gradient steps to optimize, and then following that, we'll do the refinement. So if we follow this sequence, the quality of the approximation is going to improve. So here's our initial mesh, and you can see it's just as we saw before. If we perform one refinement and re-optimize, you can see we get something that looks more like a sphere. If we perform two refinements, you can see we're getting even better. And then three refinements give us something that is really very close to a sphere indeed. This is a fairly basic problem, and so it wasn't so difficult for us to set up. But actually, many sophisticated problems in Morpho will follow the same overall structure. We're going to create the geometry of interest, create additional quantities that depend on the mesh, construct the optimization problem, optimize, and visualize. So this is your first go at using Morpho to optimize shapes. Feel free to try it yourself. Morpho is a small open source and easy to learn language for computational differential geometry, shape optimization, and more. Check out our GitHub. Thanks to the National Science Foundation for funding, and check out some more of our videos as we release them to help you learn Morpho. And thanks for watching.